Hello and welcome again. In the online lecture series, we are studying bending moment diagram and shear force diagram of different types of beams. In the earlier lectures, we have covered the bending moment diagram and shear force diagram of a cantilever beam. Uh, and in the last lecture, we also discussed about uniformly distributed load of a simple supported beam. Again, we are coming to the simple supported beam, uniformly distributed load, uniformly varying load, uniformly point load, and then combination of these and how to draw shear force diagram and bending moment diagram of all these combinations. So we'll be coming to the simple supported beam. We have just uh, a quick review of what we have earlier studied. It's a simple supported beam, and simple supported beam at point A we are having a point load, whereas at point B we are having a a roller as reaction. So this is a simple supported beam supported at both the ends, and the reactions are vertical upwards in both the cases. Roller, as I told, is are given just to support the beam, so that if they increase, so that if their length is increased due to expansion of various factors, so we see that roller support the beam and it does not harm. So we have a simple supported beam supported at one end A with point load and at one end B with the roller, and we are seeing that we have a uniformly distributed load of W, weight W per unit length. So W is the weight per unit length. So come to the next slide. We'll be having length of span is L, or clear length of the span of beam is called span. So this is called AB of span, that is clear length of beam between two supports is known as length of span. So this is L. Then we are having this reactions vertical upwards. There are no horizontal loading, so horizontal reactions are not considered right now. But if we take horizontal reactions too, then we will have to balance the horizontal reaction as well. In this case, we are not taking any horizontal reaction, only vertical reactions. And so two are vertical supports. One is vertical upward RAV, that is acting upwards, and similarly RB at the end B, that is also acting vertical upwards. So we are having W, uniformly distributed load weight W per unit length. So this is the reaction that we have calculated or already explained how to draw, how to find the shear force and bending moment at different sections. So what the shear force and bending moment is, bending moment, first of all we'll discuss shear force. So what shear force are acting from A to B at every point. Just a quick look, we have already discussed. So we are having this, we can see, as I told, the convention is if in the left section the reaction is vertical upwards or resultant force is vertical upwards, so the shear force is positive, and if in the right section the shear force is acting upwards, so that is uh, shear force negative. So this sign convention, this is the sign convention that we have discussed so many times in detail. So this is the length span. Here we are having a vertical reaction RB vertical upwards, that is WL by 2. And similarly, WL by 2 is vertical upward reaction of the point load of knife edge load, knife edge support. So this is vertical upwards and this is vertical upwards. Whereas in the mid we are having W weight W into L by acting downwards. So at this point, we are having WL by 2 vertical downwards. This is W by L, WL by 2 vertical upwards. So this both are vertical upwards, whereas the loading is done at the center point. If we convert the uniformly distributed load into point load, we'll be having a point exactly at the center, and that weight is acting downwards, vertical downwards. So first we'll start from point B. So point B, as we see in the right section, the reaction is vertical upwards because this is WL by 2, no other load is here up till L by 2. At the center point, we are having a vertical downwards load. So from here to here, only one force is acting, that is upwards. That is WL by 2 vertical upwards. So this is negative shear force. As I told, this is a sign convention. So we have taken a line AB, neutral line AB. Then we have drawn a line that equal to WL by 2 downwards, because this is, as the sign convention says, the shear force is negative. So we are coming to negative, representing equivalent shear force in the linear dimensions. So if we are having WL by 2 as 10, so we'll be drawing a line equivalent to 10 centimeter, oh sorry, 10 millimeter, because 10 centimeter will be too high. So we'll be representing the loads and the moments in equivalent dimensions. So if this is 10 newtons, if it comes out to be 10 newton, we'll draw a line from here to here, 10 millimeter, or any other dimension that is convenient to put on the paper. So this way we'll having the 10 millimeter. Then what we'll do, we'll find a load at the center point. Center point load is W into L. That means this W is L acting at the center point, and similarly you will find the reaction WL by 2 is acting on the extreme point A. So this is vertical upwards, reaction is vertical upwards. So again a force is applied at this point. So this is first point, this is second point, and this is second, third point. So we will join all the 3 points, all the 3 points. This is negative. So this way, this will be negative shear force, this will be positive shear force, and we see the sum of these two, WL by 2 and WL by 2, will be WL. So this will be acting in both the directions, because this way, this is shear force is downwards, the shear force is negative, and the here shear force is positive. So adding these two will give a result of WL. WL by 2 plus WL by 2 will give a result of WL. So WL is acting at this point, center point. So from here, we'll draw a line from here to here to here. So this is equally distributed load, that is point load or uniformly distributed load, has been equally divided into 2 parts because it is acting symmetrical to the beam. So this is shear force and nature of shear force. Now come to the bending point, the bending moment. Bending moment again, Bm is equal to 0 at B, and point A and B, both the bending moment will be 0, and bending moment will be W into L by 2 into X, Wx into X by 2, equation of beam between A and B. So this will find WL square by 8 bending moment at point C. So this is the center point, C point. Now we'll draw the bending moment. So we'll see WL square by 2 because we are having WL by 2 as the reaction into X into then WX, W by 2, WL by 2 into X in minus WX into X by 2. This is the way we are having bending moment. So this is, we can find WL by 2 into L by 2 into minus WL by 2 into L by 4 is equal to WL square by 8. So we can see that weight, reaction RB is acting upwards. Similarly, reaction ARAB is also acting upwards. And if we start calculating bending moment, so we'll be having RB into 0. This will be keep on increasing up till this point. Then we'll be having no effect of RB, and we'll be having effect of RA. From here to here, it will be the effect of RA. So this will be WL by 2 into, this is WL by 2 into WL by, sorry, length is come from here to here, we'll be having RB into 0 because RB is passing through this point and we are taking moment about this point. So distance is 0. So distance 0 is RB into 0, moment is 0, and this point distance 0, RB 0. So okay. So now it's clear that bending moment at both the point A and B will be 0. Now, what is the maximum bending moment and what will be it? First thing is that we have to find the direction, the sign convention of the bending moment. We see that it will be sagging, the beam will be bulging downwards, and the center or the curve of the center point will be coming downwards. So this way we'll be having downwards sagging, and sagging bending moment is always positive. So we have got one this point and one this point. These 2 points we have got. Now, if we take, if we talk about the whole weight is WL by 2 acting as this at this point, WL acting downwards at this point, WL acting downwards at this point. Now we take WL by 2 and WL. So WL by 2 minus the sorry WL by WL minus WL by 2 will be WL by 2. So WL by 2 will be acting at this point. If we talk about left section, we will be having a resultant force of WL by 2 acting at a distance of 1 by 4th. This one will be half. This is the half center point, and this will be acting at center point. So WL by 2 into L by 4. So this will give us WL square by 8. So we can calculate either this way or this way, that way. Both will be same. So center point will be having maximum bending moment, and that is WL square by 8. So WL square by 8 is the maximum bending moment, or at point B and point A, the bending moment will be 0. So now we have got the curve, we have got the degree of this bending moment. This is square or degree increased to the, because in shear force we are having degree of one degree of equation. So WL by 2. Now in this case we are having WL square by 8. So this is having one more degrees to the previous article. So in this case, we can see, we can find that there is a 2 degree of freedom. So there is a 2 degree of equation. We will be having a curve rather than a straight line. So this way, if you see, this will be acting, this will be increasing and decreasing as per the square of L. So this way we'll be having proportional. So bending moment will be proportional to the square of length. So when the bending moment, when the length is increasing up till this point, this is the maximum bending length, this is the length for maximum bending moment. So this will be having that, this will be increasing in proportion to the square of the whole uh, of the whole equation. So we can see that when there is a square or second order of equation, the diagram is curve. The diagram is a resultant curve. So we'll have to draw a curve from here to here, and similarly from here to here. So this is the bending moment diagram of a simple supported beam loaded with uniformly distributed load. Now we'll come to the we'll come to the example that we have already discussed. Now let's again discuss it. This is A point, this is B point, this is A distance direction, and this is B. Uniformly varying load is again uniformly varying load. Again, you can see at point B there is no load, and it is maximum up to point A. And we have discussed earlier in case of cantilever beam that it acts at 1 by 4th of the beam. So we can see here, this is the 1 by 4th, this is center point, this is the beam. So at the right hand side, we are having a vertical upward reaction, that is negative shear force. So this is negative shear force. Then we are having left upwards, that is positive shear force. This is positive shear force, and the whole shear force is WL by 6, and this is WL by square root of 3. This is the point. This is the point at which, if we convert this whole load into, that is L by square root of 3. L by root of 3 will be, if we multiply by, this is 3 L by root 3. So this is the distance at which it will be acting if we convert this uniformly varying load to the point load. So this point will be, this is distance is L by root 3 and this is L minus L by root 3. So this will be having distance at which it will be acting. And now we can see here that this is WL by 6 is the reaction. We will calculate. This is WL by 3 reaction. So from here, this is negative. From here, it will keep on decreasing, keep on decreasing, keep on decreasing. Point L by root 3, and it will change the direction and will be positive from here to here. So we can see this is the negative shear force, this is positive shear force. This is a plane, this will be a plane curve rather than a straight line. Okay, so we'll be discussing more. Then we have bending moment. Bending moment, we have got to know the shear force. Then we have bending moment. Simply multiplying with the distances, we'll be getting both these points will have zero bending moment because the force A is passing through it and the distance is A 0. Similarly, B into 0, WL by 6 into 0 and WL by 3 into 0. So point A and B will have zero bending moment and this will be point L by root 3 and this will be having maximum bending moment, and so we multiply L by square root of 3 and the force is shear force is W L by 3. So multiplying this we will be getting maximum bending moment. Now come to a problem where we have clubbed with three types of loading. One is uniformly distributed load, another is point load, and the third is moment of a couple. So this is having, we have a beam of AB of 8-meter span. Then we are having 2 meter and 2 meter uniformly distributed loading, point loading, 2 meter, 2 meter. Okay. Now between A and B, we are having a uniformly distributed load 3 kilonewton per meter. So first we'll talk about shear force, what will be the reactions, and then we are having A, B, C, D. So the reactions can be named as RA, RB, RC, and RD. So these are the points, these are the critical points where loading and support are done. A and D are the supports, whereas B and C are the loading. Point loads are acting downwards, 80 kilonewton and 50 kilonewton. Then we are having a moment of a couple of moment 40 kilonewton meter is also acting. The whole span of the uh, beam is 8 meter. Now come. So we are calculating. Now we have to find the vertical downwards reaction. You can see 80 kilonewton plus 50 kilonewton plus 30 kilonewton multiplied by 4, that is 120, acting in the center, that is again 2. 120 kilonewton, 120 kilonewton weight point load, because of this uniformly distributed load being converted into point load, will be acting at center of the A and B, that is 2 meter, and this will be 2 meter. So this will be having 30 into 4, that is 120, acting at this point. So we are having now 1 point load, 2 point load, and 3 point load. 80 kilonewton, 50 kilonewton, and 120 kilonewton downwards. Similarly, we will be taking the account RA plus RD, RAV or RA plus RD must be equal to 120 plus 50 plus 80, that is 250. So 250 divided by 2, so that must come 125. So this is RAV. RAV is 130. Yes, 130 and 200 kilonewton we can calculate this way: 30 into 4 into 4, 30 into 4 into 2, 30 into 4 into 2, 30 into 4, that is 4 meter span, 120 into 2, 2 meter. So moment at A, we are finding moment at A. So 30 into 4, that is 120. and acting at 2 meter from point A, 30 into 4, 120 into 2, 240, plus also acting downwards 50 kilonewton multiplied by 4, 50 into multiplied by 4 plus 40 is directly added because it is already a moment. At this point, P point, we are having 40 kilonewton couple of moments. So this is directly added 40. It's not needed to be multiplied since this is not a force, this is a moment. So this is directly taken. We are calculating moment. So this is directly taken and it is not multiplied by the distance, whereas we are having 80 into 6. 4 plus 2, that is 6. So 80 into 6 minus RD is acting upwards. So this reaction, so this will be taken as minus because all these points, this uniformly distributed load, this couple, these 2 point loads are acting vertical downwards. This couple is acting at this point B. So these are taken one direction and the support reaction is taken in anti-clockwise in other direction, that is negative. RD multiplied by 4, RD multiplied by 8, sorry. 2, 2, 4 or 4 plus 8. So this way we are having a reaction 30 into 4 into 2 plus 50 into 4 plus 40 plus 80 into 6 minus RD into 6 equal to 0. This way we will be finding reaction RD because everything is given. Sum of all the moments must be 0. So all these are kept equal to 0. So this way we will find RD. RD is 120 kilonewton. We have already found this 250 is the vertical downwards reaction. So RD is 120. So another will be 130 kilonewton. Now we have got two reactions, RD 120 and R AV as 130. Okay. So now come to the shear force. We'll see shear force at D, shear force at DL, right side, left side. So shear force at point D, shear force at point D, right side will be 0. Shear force at point D, right side will be 0. The shear force at point D, left side will be minus 120 kilonewton, right? Because this 120 is vertical upwards. If you take the right side, 0, left side, 1. Come to the point C, we'll be having reaction RAV plus RD. No, I talked about this is RAH. Sorry. We have got the reaction RH horizontal. We are not talking about horizontal reaction. RD, RAV, therefore RAV. Yes, yes. Shear force at DL 0 minus 20. Then C point rightwards to the C point is again, there is no force from here to here except this RD. So from here to here we will be having only one. Then at this point another vertical downwards load is added. So this was minus upwards. This will be added to this. So this was 120, 120 minus 80. So we'll be having 40. Then come to this point, another 50 is added. That means 40 plus 50, that is 90 added. Similarly, come to here, and this point will be finding another 120 because 30 into 4, 120. So 120 is also acting at this point. So 120 will be added again, and this will be the highest. This will be the 130 RAV. So this can see this is baseline AB. So we are having 130 vertical upwards, 120 vertical downwards. When we are coming from D to C, there is no other force except D up till C. So this is a straight line. At point C, point load of, we see a point load of 80 kilonewton is added. So when this is added, it will be coming down. So we can see 120 to 80, it will be decreased. Then it will be having from, because from C to B point we are not having, from C to B we are not having any addition except at point B we are having another 50 kilonewton downwards. So the 50 kilonewton downwards is added. So this will be 50 at this point and 40 plus 10. This is the point from here to here because this is 40. and we are adding 50. So from here we have to go verticals for 10, another 10 kilonewton. Then we'll see there is no other force from here to here, no point load except this uniformly distributed load. So uniformly distributed load is represented by a inclined line. So from here to here we will join these 2 points by a straight line, by an inclined line to the horizontal axis AB. So this is the shear force diagram of this complicated problem. We have calculated the shear force. In the shear force diagram, bending moment is not taken into consideration because bending moment is already given, and bending moment is acting only in for the consideration of bending moment diagram, not for shear force diagram. So shear force diagram will not have any effect of bending moment. But in case of bending moment diagram, we'll be finding like this. So we can calculate here to here it is 0. Then from here to it is 240 Newton, 240 kilonewton meter. We have calculated this way. We can find 120 is the reaction vertical upwards. 2 multiplied by 2, 240. Then we are having 120 into 4 minus 80 into 2 because 80 into 2 is acting downwards. So this is again added. This is no sorry. This is added. Yes, this is added. 160 plus sorry 480, this is 480 minus 160, this is 320. You can see the bending moment. In case of bending moment, this is acting vertical upwards, this is downwards. So bending moment because of RD will be positive, whereas bending moment because of 80 kilonewton will be negative. So this is again RD, that is 120 multiplied by 2. Sorry, we are taking about at this point 120 multiplied by 2, that is 240 kilonewton. That is point C. This point C. 120 multiplied by 2, 240. Then come to this point. 120 multiplied by 4, that is 480. Then this, because of this, it will be downwards. So we can deduct. We take bending moment at point B. This will be RD multiplied by 4 meter. Then bending moment because of this are 80 into 2. This will be negative. This will be deducted. So 480. This is 480 minus 160. This is 320. Similarly, 120 to 4 into 80 into 2 minus 40. Another minus 40 is acting at this point, we can see. So if we add this plus this, so this will be 40 kilonewton. So direction of 80 kilonewton, 50 kilonewton and 40 kilonewton will be vertical downwards. So this will be having shear bending moment as this much. We have calculated 280 and then at 0, 240, 320, 280 and 0. Now let's draw. So again it is clear that condition will be sagging, and when sagging is there, the bending moment is positive. So from here to here will come to 0. We'll start from 0 up till 320, 240, then we'll come to 240, then we'll come to 320, then we'll be having vertical downwards negative, and this is 40. Then we are having a parabolic curve because from here to here we are having a uniformly distributed load. So because of uniformly distributed load, the shear force, so bending moment will be a parabolic curve from here to here. So this is the bending moment diagram. This is positive from here to here. I think this is right now it's bending moment diagram and shear force diagram of point load and of simple supported beam and the cantilever beam are clear to you. So still if you are having problem in understanding the concept or anything else, you may get in touch with me on my phone number. My phone number is 9069360400. So I am signing off for the time being.